Alright, guys, happy Friday. Go ahead and get your notes up. We're going to pick up with rotation. So, when last we spoke, we were discussing the fact that the Earth rotates on its axis. We gave the analogy like a top or like a dreidel. When it spins, that axis of rotation is imaginary. Unlike a top where you can actually hold it, Earth's axis is imaginary, and as we spin around on that axis, our speed actually goes from near 0 kilometers per hour up at the pole all the way down to almost 1,700 kilometers at the equator. Now, that spinning, they didn't always know about. There was a big argument with the geocentric model that the Earth was actually stationary and everything else was moving around it. When we got evidence from from Leon Foucault, we were able to see that because his pendulum was swinging back and forth, the change in direction they associated with the rotation of the Earth underneath. In the text, you guys can actually click on a little video and see how that works. I'd encourage you to do that. The other line of evidence that supports the fact that the Earth rotates is what's called the Coriolis effect, or the deflection of winds to the right, or curvature to the right in the northern hemisphere and to the left in the southern hemisphere, because the Earth rotates. Now, let's stop and break this down for a second. If you're at the equator and you're trying to throw a ball all the way up to the North Pole, you're moving at almost 1,700 kilometers per hour. As you throw that ball, right, it's adjusting to the area that you're in and would be moving a lot faster as it moves up to a point that's almost near 0 miles per hour. Because of that speed that ball's being released with and the motion to the right, as the ball were to move up toward the North Pole, it curves off to the right. If you think about it from the other direction, throwing a ball from the poles, from the North Pole down toward the equator, imagine, of course, you're Superman, you can actually throw it that far. When you release that ball, the target that you're aiming at, by the time the ball gets all the way down there, would be way far off to the left. So as you're standing there at the North Pole, you're going to see the ball make this apparent deflection to the right. We'll discuss that a little bit more, but I just want you guys to get a brief introduction to the Coriolis effect before we continued. So moving on from proof that the Earth rotates, how does that actually break down? Well, the Earth has to rotate 360 degrees every 24 hours. And I did the math for you. That's 15 degrees per hour, and or hour being 60 minutes. That breaks down to about 1 degree every 4 minutes. So when you go out there and you're watching a sunset, you're starting to lose the sun. You can, when it hits the near horizon, you have about 4 minutes before it completely disappears. How does this break out on the globe itself? Well, we break up that 24-hour period into 15 degrees, and that's actually how they're going to come up with the designation for time zones. So I think we've belabored rotation. I want to take it a step forward and think now the Earth's rotating, right? 360 degrees, 24 hours, everybody's happy. Well, it's going to do this all year long. So how long is 1 year? Well, it's the amount of time it takes for the Earth to complete one orbit, or the nicer word we like to use is one revolution. Now, we've discussed the Earth in chapter 3, so now that we're in chapter 4, we're going to add a little more detail to it. So we said that Earth's year is actually 365.24 days, and therefore that explains why we need a leap year every 4 years, and why we don't have a leap year on centennial years. Because remember that 0.24 is 100th less when you start adding that up over the course of 100 years, they actually don't need to add the day. We went through that before, I'm just reminding you. Now, if you remember back to Johannes Kepler, Kepler said that we move in an elliptical orbit as we move around the sun, and we actually will vary in speed as we move through that orbit. Part of that varying speed is due to the fact that the sun is not perfectly centered in our orbit. And if you look in this diagram right here, I know that was a little crazy, I apologize, should have warned you. You can see that there's a point where we're closest to the sun, right? You look off to the right and it says 147 million kilometers. And then on the left it's saying 152 million kilometers. So when we're closest to the sun, we're going to call that perihelion. I'm going to just close this down just a little. Right? We're going to call that perihelion. And that actually happens in January. So we're approaching perihelion. We're approaching that point in the Earth's orbit when it's closest to the sun. If you look on the left, when we are furthest from the sun is actually called aphelion or aphelion, depending on how you want to say it. I always think ap, away. It might help you. Peri translates to near, for those of you that want to be able to break down the words. And then helion would mean sun. Later on in this chapter, we're going to talk about the moon, and you'll learn about apogee and perigee. So G being the term for the moon. You guys are going to start to see a little bit of a pattern here. So I went ahead and adjusted that for you, because some of y'all are going to need to put some notes down here. So perihelion, key point here, we're closest to the sun on or about January 3rd. So it's counterintuitive. You're all probably sitting there going, but wait, it's cold in January. That has to do with the tilt of Earth's axis, which we're going to get into in the next part of this lesson. So we're closest to the sun in the winter. We're furthest from the sun in the summer. And theoretically speaking, if it was the other way around, our winters would actually be a little bit colder, and our summers could theoretically be a little bit warmer. But I think we like the temperatures we have. Some of you might disagree, but oh well. All right, this does not cause the season. So go ahead and highlight that in your notes, right? Does not cause seasons. Because as you're going to find, the tilt of Earth's axis causes the seasons. Yeah, I'm pretty good with this highlighter, aren't I? I know you're all impressed. Now back to a little bit of Kepler. As we said before, a planet is going to vary in its speed as it moves around the sun. Again, because when it's a little bit closer, like during perihelion, we actually revolve a little bit faster. And then when we're further away during aphelion, we actually slow down a little. Well, the average speed of revolution is 27 kilometers per second, or for those of you that need the American system, right, about 17 miles per second. Go ahead and do the math. You start realizing that's pretty stinking fast. But that variation has everything to do with the location of the sun and its gravitational pull as we're moving around. And then when we go out into that further point, the gravitational pull is just slightly less, so we don't move quite as fast. And now, for the moment you've all been waiting for, Earth's tilt causes our 4 seasons, right? Our summer, our winter, spring, and fall. Although, finally, I think we're starting to see fall as we're near in the middle of what would normally be fall. This is all because when the Earth's axis is tilted at 23.5 degrees, I'll say that again, 23.5 degrees, there's going to be a portion of time where Earth's axis is tilted away from the sun, and a portion where it's going to be tilted toward the sun. So I'm going to give you guys a second to just think about that. If it's tilted toward the sun, we'd expect it to be just a little bit warmer. And in fact, that would happen, as it says in the notes right here, during the summer. Then you see in the winter, we're tilted away from the sun and start thinking, wow, winter, that's when we're a little bit colder. So if we're tilted away, more insolation is actually going to be striking in the southern hemisphere. And for any of you that know about the southern hemisphere and their seasons, they're actually reversed. So while we're chilling during summer, they're actually chilling because it's their winter, and vice versa. And now for the visual learners. We got a nice little picture for you. If you look here, it's showing 4 key positions, what are known as either the equinox or the solstice. During the summer solstice, June 21st, 22nd, the most direct angle of insolation is going to be striking on what's known as the Tropic of Cancer, which happens to be right over here. Right, this up here has actually got everything labeled, but I want to point it out that the sun's rays, 90 degrees of insolation coming in right at the Tropic of Cancer. So 90 degrees of insolation is going to be the most concentrated insolation striking Earth's surface. The greatest concentration means it's probably going to be the warmest point on that given day. So we're going to learn a little bit more about angle of insolation in our next lab. But for right now, let's just go with this concept. June 21st, 90 degrees of insolation striking on the Tropic of Cancer. Now, I know some of y'all are like, Tropic of Cancer, where'd they get that name from? Well, because it's kind of in a tropical region. And on June 21st, if you're into your zodiacs and astrology and all that great stuff, that is when Cancer changes. So your sign, if you're born on June 21st or later, you'd be a Cancer. When you look in the opposite direction, right, when you look over on the winter solstice on the right, the most direct angle of insolation is actually going to be striking at 23.5 degrees south latitude, or what's known as the Tropic of Capricorn. Now, for the late December babies in the room, you know that Capricorn replaces Sagittarius on June 21st. So that's where they got that fun name from. That happens to be the opposite of the summer solstice. So where you're getting 90 degrees of insolation striking in the northern hemisphere, on the winter solstice you have 90 degrees of insolation striking down in the southern hemisphere. Let's look at a couple other things in this diagram though. I'm going to draw attention to this line right over in here. If you notice, the right half is really dark. The left half is more illuminated. Well, in fact, on December 21st, the North Pole, or anywhere above around 66 degrees north latitude, is going to have a really short day, almost to the point of no day at the North Pole. So if you were chilling at the North Pole on December 21st, it's total darkness. Yeah, I paused for a reason. First time somebody said that to me, I was like, are you serious? Total darkness, like no sunlight? How do they even know it's day? Because they got a watch, that's how. In the southern hemisphere, the South Pole has 24 hours of day. So those of you that can't sleep when the sun's out, like, don't hang out at the South Pole on December 21st. But let's look back on the other side, on the left. Right, I'm going to draw that line again. Here you see on June 21st, the North Pole has 24 hours of day, and the South Pole has 24 hours of night. So I'm pointing these things out because you're going to start to see a little bit of a pattern. If I have to go from 24 hours of day to 24 hours of night, or 24 hours a day to 0 hours of day, right? There must be like a break point, like what's a good number between 24 and 0? I know I just asked you to do math. I apologize. That's 2 days in a row. 24 divided by 2 gives us 12. 12 seems like a pretty good number. Well, wouldn't you have it that 12 would mean like equal day and equal night, right? I'd have 12 hours of day and then 12 hours of night. That sounds pretty equal. That might happen if the 90 degrees of insolation, rather than hitting one of the tropics of Cancer or Capricorn, but rather strikes right on the equator. Equal day and night, 90 degrees of insolation on the equator. I wonder if I can come up with a good name for this day. How about equinox? Wouldn't you know it? They actually call this the vernal equinox and the autumnal equinox. Almost like it makes sense. I don't know. I'm going to let you guys think about that one while you go ahead and fill in your notes. Sorry about that. It took me a second. So, as you guys read it down, you're seeing on the summer solstice, June 21st, most direct angle of insolation, or 90 degrees of insolation, striking the Tropic of Cancer, 23.5 degrees north. And every point above 66.5 degrees north would have 24 hours of sunlight. And any point below 66.5 degrees south would have 24 hours of darkness. As you guys are going through this, I'd like to point out that during the winter months, for either the summer or in the northern hemisphere or in the southern hemisphere, remember they're inverse. So let's talk about winter in the northern hemisphere. That falls around December 21st. If you're living in places like Alaska, in places like Greenland, a lot of these high northern latitude areas, people struggle with like things like depression because it's just dark for so long. And they've actually scientifically proven that you need sunlight to get vitamin D to keep people happy. So depression is definitely an issue. But even where we are in New York, they find that during the winter months, there's less sunlight out. People are not out and about as much, and oftentimes in the winter months, people struggle with depression. We'll talk about that a little more another day. When you look a little bit further down with the vernal equinox and the autumnal equinox, this is when that transition period starts. So for us, since September 22nd, our days have continually gotten shorter and shorter. We've had less and less sunlight. And case in point, when you guys are getting on the bus in September, well, great, I can go home, I can play outside. I mean, theoretically, most of you probably just hang out inside. But for me at least, I could go home and like take the kids to the park till 7, 8 o'clock at night. Now, I get out at like 5:30. It's already getting dark by 6. The kids aren't really supposed to be playing outside anymore. And you're going to see that trend. We'll talk a little bit about daylight savings next week, and you guys are going to kind of understand why all that goes into effect. Now, the last little part with your notes today is going to talk about Earth's precession. So we're going to have 3 different cycles that the Earth's axis and rotation go through. Today we're going to just look at precession. So again, if you think about a top spinning or dreidel spinning, oftentimes while it's spinning, its axis is going to kind of have this little wobble to it. Right, so it's spinning, but maybe it's pointing toward the side of the room, and then toward the front of the room, then toward the other side, then toward the back. That motion is referred to as precession. And it's caused by the gravitational pull of the sun and the moon on the Earth. So that little precession can alter our seasons, the lineup of the seasons, and they found by looking at things like ice cores and looking at the rock record that this precession tends to happen in a cyclical pattern that takes about 26,000 years. If any of you are like, what? Don't worry, I'm going to go over this again. But at least as you're going through your notes and as you go through the reading and the homework, hopefully you have a little bit of an understanding as to what you're looking at. All right, so you guys definitely got off pretty easy last night because with everything going on, I forgot to hit save for your homework assignment. So I want you to use the rest of the class time to be working on your vocabulary. I'd like for y'all to try and finish your vocabulary between the rest of the period and over the weekend. We'll pick up with some reading and outlining come Monday. The labs, if you already turned it in, I'm actually going to go and just wipe them out and have you guys officially turn in your labs on Monday after I give you about 5 minutes just to clean up some of the details. I figure that should make it a little bit easier. I hope you all have a great weekend and thank my colleague for spending the time with you today. Apologize if this lecture was a little boring. All right. Enjoy your weekend, guys.